We will start now with a section of presentations of current projects, ongoing projects. And we will start with a project founded by the Baltic 2020 Foundation. And the study is now entitled Anoxic Sediment Bind Phosphorus After Aluminum Treatment and is presented by Linda Kumblad and Emil Rydin. Please, and I will give you a warning side, maybe 30 minutes, that you please keep 15 minutes for the presentations. Then we have 5 minutes discussions. Please, the floor is yours.
Okay, thank you very much. Again, can you hear me in the back? Great. We're glad to get this opportunity. It's actually the first time we present a project in this type of forum. I and Emil are working for Baltic Sea 2020, which is a private foundation. And since 2011, we run the project For a Living Coast. And the aim with that project is to demonstrate that it is possible to restore heavily eutrophied coastal areas and achieve a good ecological status again. And this project is performed in Björnö Bay, or Björnöfjärden, in Stockholm Archipelago. And that bay was really one of the most eutrophied bays in Stockholm County before we started. In the project, we perform measures to reduce both external loads in the catchment area and internal loads. But we also monitor the effects of the measures that we do and evaluate the effectiveness. Björnö Bay, this is maybe a poor map, but it's a map of the bay. It's enclosed and has a limited water exchange with the water body outside. But still, the salinity is around 5 per mil in this area. It has severe eutrophication symptoms in terms of anoxic bottoms. The shaded area here is the anoxic bottoms. So basically all sediments below 6 meters are anoxic all year round or hypoxic. In 2011, when the project started, the majority of the phosphorus load in this area or in the water came from previously released external loads to the bay that was recycled from the sediment. And in the project now, we have full focus to reduce these external inputs. But these measures are not, the effects of these measures are not visible yet. And in this presentation from now on, we will concentrate or focus on the internal measures that we have done, the aluminum treatment. And Emil will give the theoretical background on this measure.
Yes. This illustration is supposed to show you the development of eutrophication in the Björnö Bay over the last century. And the left graph here shows the first half of the century in the Björnö Bay. Here we have a balanced input of phosphorus and binding agents, the yellow dots. And binding agents might be iron, aluminum, or calcium. So here we have enough binding elements to bind all the phosphorus that are entering the sediment. But then during the second half of the century, the phosphorus load increases several times. But the load of binding agents are most likely about the same. So there is not enough binding capacity in the bottom to retain all the phosphorus. And we start to get this release, the internal loading of phosphorus from the bottoms. And this is even more enhanced by anoxia, and we lose the binding capacity of iron. So what we did was that we added more binding agents, more aluminum into the sediment, to have a balance again of elements that bind phosphorus. So we did cut off the internal loading. We broke this vicious circle. So Linda, how was this done?
Yeah, the aluminum treatment, that's a well-known lake restoration method, but has never been done in brackish water or marine environments before. When the actual treatment took place, the boat on the surface lowered down plastic tubes into the sediment where an aluminum solution was injected to the top 10 centimeters. And the dissolved aluminum in that solution bind the phosphate, the mobilized phosphate, and it bind it permanently. The substance that we used is the same substance that is used in water treatment plants as a cleaning water agent. And we performed the treatment stepwise in the summer 2012 and 13. And now, 1 or 2 years after this, we see that it also works in brackish water environment. And Emil will guide you through the results in the sediments and the water in a couple of graphs.
Yes. This graph shows you the outcome in the sediment. Here we have the sediment surface and down to 20 centimeter down in the sediment. And we have a phosphorus concentration on the x-axis. And the total phosphorus concentration in the sediment before treatment was like this. A small increase towards the sediment surface. This is a typical profile for a coastal sediment. 2 years after, now we have more or less doubled the total phosphorus content in the sediment. And this increase is explained by increase in aluminum-bound P. So what we see is diffusion of dissolved phosphorus that is caught to the added aluminum. And the main flux is most likely from the deeper sediment, but also some diffusion downwards to these aluminum-enriched layers. So now know if we have good binding capacity in the sediment, what will happen in the bottom water. Here we have the project period starting from summer 2011 and until now. Here we have the dissolved phosphorus in the bottom water. And here we have high concentrations and periods of low concentration. And this is due to periods of mixing and periods of stagnant bottom water when we have increase in concentration. And here we have the periods of treatment. And to summarize, after the treatment were completed, there is no more accumulation of dissolved phosphorus in the bottom water. And then the water column, the average total phosphorus concentration in the whole water column. Again, the project period and the 2 treatment periods. And the red here is a reference bay we have to compare with. And again, before treatment, we have rather high total phosphorus concentrations in both the reference bay and in the Björne Bay. After treatment, we are about a 50% reduction compared to the reference bay. And Linda, other effects of the treatment?
Yes, as you saw, the response in the water column and sediment was both quick and quite strong. The recovery of the ecosystem, however, is much slower. But we already see some effects or indication of improvements. For instance, the phytoplankton biomass has decreased as a consequence of the reduced availability of phosphorus. This, in turn, has increased the water visibility. The Secchi depths have increased. And that has also influenced the bottom vegetation that we now see deeper than before. Although we saw less anoxia, a little bit less anoxia in the sediment during the summer period last summer, we don't see any improvements in the bottom fauna yet. And that's mainly because there is very, very large loads of organic material still to be mineralized. That will take a couple of years, I guess, to see a response in. But we expect more and clearer results in the ecosystem in the years to come. Now, I guess that many of you are wondering whether there are any risks with aluminum treatment. And as I said before, we have a monitoring program, and we haven't detected any side effects yet. And actually, we are not expecting to find any either, since the aluminum treatment is an enhancement of a natural process. Although it is known that aluminum can have a toxic effect on aquatic organisms, in fish, for instance, but that occurs when aluminum is there in dissolved as a dissolved species, and also in high concentrations. And aluminum is only soluble, or the solubility is very low of aluminum when the pH is around neutral, and that's the pH that we have in the Baltic Sea and in the sediment. And on top of that, the buffer capacity is good. During the actual treatment, we saw an enhancement of the aluminum concentration in the water, especially in the bottom water. But looking at the whole project period, we cannot now see an increased aluminum concentration compared to prior to treatment. And yeah, to summarize, although we don't see any effects or expect any effects, we still think it's very important to follow this up, continue the monitoring, evaluate. Now, for instance, we are analyzing aluminum content in biota to see whether this might have any potential side effects. But in a few years, if it turns out that we only get positive results, it might be very interesting to know the costs of this.
Yes.
Emil.
So in the Björnö Bay and the area treated, that was close to 1 square kilometer, we so far have sorbed about 1 ton of phosphorus to the added aluminum. We expect the total store of phosphorus in the sediment to be mobilized and released to be 4 tons. And we have enough aluminum there to bind also the future mobilization of sediment phosphorus. So costs. In the Björnö Bay, here we have divided the cost into the cost for the chemicals and the application cost. And the application cost in the Björnö Bay includes a lot of development cost for the machinery used. So we have a rather high figure for the removal cost per kilo phosphorus. The company Vattenresurs AB estimates a larger bay, a much lower application cost, ending up with somewhere between 300 or 400 Swedish crowns for binding 1 kilo of phosphorus. So, conclusions. After the aluminum treatment, anoxic sediment bind the phosphorus again. We are in the middle of evaluating both binding efficiencies, but also, as Linda said, potential side effects. So we are not ready to support or suggest another site to be treated yet. But we think we have promising results. And the last slide is, what is the next step, way forward? This is a map showing the Stockholm archipelago and the Finnish archipelago. And the red areas here represent sediments with high concentration of mobilizable phosphorus to be released. So there is areas where there is more phosphorus to be released than others. The yellow and blue areas represent areas with low concentration of mobile phosphorus. So what more can we learn about the phosphorus turnover in the coastal zone, the load, retention and release? Are there hotspots of phosphorus release? And what are the potential for dealing with these hotspots? And what would the effects be on a Baltic Sea scale if these kind of hotspots were terminated? And with that, I think we're done.
Yes. Thank you.
Thank you, Emil and Linda. I am pretty sure there will be a lot of questions now. Please.
Hi, Steve Hinton from the Sustainable Economy Foundation. I'm a little bit interested in prices. 350 crowns per kilo is to remove phosphorus. Have you any idea what it costs, by comparison, to remove phosphorus completely from sewage water? Are the prices comparable? I mean, is prevention more costly than cure, or is cure cheaper than prevention?
I don't know the actual figures for nutrient removal in a sewage treatment plant. Is there anyone in the audience who know that?
The last percents are very expensive to remove.
Yeah. So that is perhaps one answer. If you want to remove the last 96 or 97%, that is probably more expensive than these figures.
Are there more questions? I'll give you some time to think about. Maybe I have one. You said, yes,
Yeah.
Peter.
Thank you. On a technical kind of level, how well developed is this technique? Can it be? When would it be able to go on a larger scale?
It is now developed to reach the bottoms down to 25 meters. That were the maximum bottoms we had in the Björne Bay. I guess there are other challenges if you're on a more open water. So that is a question actually the company should answer. What they can see is how fit is their technique for larger projects.
Okay, thank you.
Actually, what was the technique? 1 tube, 5 tubes, 20 tubes?
The technique is a large bar in steel that is lowered above the sediment, and then they have tubes, plastic tubes, and then the aluminum solution is mixed down into the top 10 to 15 centimeter of the sediment, and they have then a good positioning system, so they know exactly where they are and have been. So they're able to get the dose you want at a specific site. The width of the, I think we have a member of that company here, Lars. What is the width of the? Yeah.
The equipment that we used in Björnefjärden has a working width of 10 meters, but there's no problem to widen it if there are larger areas to cover up.
Thank you.
Okay, I think I can allow one more question.
Okay, thank you. Just concerning the acidification of the oceans, will that affect the solubility of the aluminium, and is that a potential problem?
If pH go down to 5.5, then aluminum, both the natural one and the added one, will start to dissolve. But then that is a really acidified system.
Okay, one more short question.
This is a very quick one. How long does the effect last does it last like forever or for a certain amount of years or?
What we see from lakes that's been treated like 30 or 40 years ago, it seems to be a permanent binding. So we expect it to be there forever.
Okay, thank you. Thank you, Linda and Emil. So now comes our next presentation by Professor Anders Stigebrandt from Gothenburg University. And this project is entitled Oxygenation of Anoxic Bottoms as a Method to Decrease the Internal P Load and the Eutrophication of the Baltic Proper. Please, Anders.
Ja, hörs jag? Ja, det gör jag. Äntligen, höll jag på att säga. Vad kul att man ska få prata om såna här saker. Äntligen, vad kul att få prata om syresättning av Östersjön. Jag är professor i fysisk oceanografi. Oh, excuse me. Finally. I'm glad to be here to speak about oxygenation of the Baltic Sea. I'm a professor of physical oceanography and have worked with the Baltic for a long time. And I came into the business of eco-engineering in 2004, actually, when Miljövårdsberedningen asked me to investigate whether sea-based methods may be used to combat the increasing eutrophication of the Baltic Sea. And a solution was suggested with dams at the sites, where pumped up water in the dams, oxygenated it, and put it back again. But the pumping costs should be too expensive, so that was not a feasible solution. And in 27, Bo Gustafsson and I published a paper where we actually suggested oxygenation on the large scale, and we were inspired by nature, which actually oxygenated the Baltic in the end of the 80s and the beginning of the 90s. And the phosphorus content sank, and we believe that that was due to the increased areas of oxidized bottoms that could bind phosphorus. And we got a big project, the box project, starting 29, ending 2012, where we made an experiment in the Bifjord, and we studied a lot of environmental effects. But in this project, we also developed a P model for the Baltic, showing that the internal P source from anoxic bottoms is huge. And I will show that. And the model shows also that the Baltic proper may be restored by oxygenation of the deep water. And then I had a smaller project with the engineers, calculating costs for pumping, and also making numerical experiment in the Bornholm Basin to see what would happen with cod recruitment if one should oxygenate that basin. And all projects has got funding from Mistra, Vinnova, Swedish EPA, Swedish HAV, NEFCO, DIB. Thank you very much. I think Bo showed this earlier, this spreading of dead bottoms. And he didn't show this one. This is the volume of anoxic water. And the scale is here, 1,000 cubic kilometers. And as you can see, the volume has increased quite much from the end of the 90s. And the light blue is hypoxic volumes. And not even a major Baltic inflow may pay the oxygen depth. This is a huge oxygen depth here. So as Bo also said, that the new simulated inflow would create better conditions at the bottom for a few years maybe, but higher up the problems remains. And you can see no signs, small signs of larger inflows during this period. This is the annual external supply of phosphorus from 1950 to now, almost. And as also Bo said, it had a maximum in the 1980s. It's almost half now. And then you would expect, if nature is reasonably linear, that the concentrations should have gone down. But nature isn't always so nice. You can see the phosphorus content here, below and above 60 meters. And this is from 1970 to 2010. And there is no decrease, there's actually an increase in the phosphorus content. And if you plot this phosphorus content below 60 meters with the area of anoxic bottoms, you can see that there is a very nice correlation between those, suggesting that anoxic bottoms are P sources, and that is known from lakes and has been also hinted at least for the Baltic earlier. But if this is true, that also implies that oxygenation of anoxic bottoms will turn off the internal P source. So in the box model, in the box project, we made this box model, so-called Folomide type model. But the new thing compared to earlier models of this kind was that we introduced the internal source. We have a small source from Kattegat, the external source which is decreasing. And this is a winter surface water concentration. I will just show that you can formulate an equation for the change of storage of phosphorus as a function of the external source, internal source, the Kattegat source, the Kattegat export, and the internal export. And it turns out that all sinks are proportional to the winter concentration C1, which allows you to write this nice equation for the concentration of phosphorus, winter concentration of phosphorus in the surface layer with all the sources in the denominator and the sinks down here, and with a small correction for changes in the storage. We used this equation in a paper to determine the internal source, which was considered proportional to the area of anoxic bottoms. We used the data from the Baltic for 2 years, 1980 and 2005, when the anoxic area was 20,000 square kilometer and 40,000 square kilometer, and the external source was 60 and 35,000 tons inside the beds. And the result we got was that the equation can be fulfilled if the internal source was 45 almost 46,000 tons per year in 1980 and increased to 92,000 tons in 2035. This means that nowadays the internal source is 3 times larger than the external source. Those crowns are not original. Were added on the. It seems like a silver stamp, real stuff, but it's not mine. The total source in 1980 and 2005. This is the external source, internal source, and the Kattegatt source. And counting backwards, it looked like this in 1955. So we had this increase in the external source to 1980, and added on top of that a large internal source. So the question is, what will happen here? So again, there is the equation. And for steady state, the solution is linear. This is 2005, 1980, and so 2005, 1980, 1955. So obviously the concentration in the Baltic has moved due to the increased load, and it didn't go down due to this decrease, but it continued to increase due to the internal load. And 2030 will be about as 2005 if we don't do something with internal load. Nature isn't capable to do that yet, at least. The influence this year and the development the next couple of 2 years will show that. So what we all want is to get rid of that, maybe by natural circulation or by doing something. And if you do something, if you remove this internal load by oxygenation, you actually will get a system in balance with the external and Kattegatt load, which now, at least 2030, will be lower than 1955. So it will be 1950, end of 1940s. Down here, with maybe a concentration in the surface instead of 1, now of 0.25. And can that be done? We made this is from the Byfjord experiment, where we oxidized the deep water in the fjord, which is almost permanently anoxic. We chose the Byfjord because it's quite similar to the Baltic Sea nowadays. Almost permanently anoxic sediments. And this was before the experiment started, and the technique here is photos from sediment profile image, and this is taken by marine monitoring, and Rutger Rosenberg is one of the maybe the inventor of the method. And 60 months after the oxygenation of the deep water, we got this with an oxidized surface layer. There had also been colonization of the sediment, and even burying animals in the sediment only after 16 months. When we started, people said, no, you can oxygenate the water, but not the sediments in that short time. But they were wrong. And actually, you can see similar things in the Bornholm Basin, which is a basin that these days naturally switches between oxygenated and anoxic conditions. So how long time will it take to restore the Baltic Sea proper? I think the first year of pumping will 1 year we were spent to pay the debt, the oxygen debt, the first year. And the second year you can start oxygenating the water. And after 1 year with oxidized surface water, like in the Bifjord, the sink will be cut off. And the sink is now about 130,000 tons. And if you cut off that, you will have a large net decrease of phosphorus in the water column. And so year 2, you will see a decrease of about 15%. And if that continues, it will take about 10 years to get equilibrium with a new total supply, which is is the external supply plus the Kattegat supply, which then is 35,000 tons or something like that. And the nice thing here is also that since the surface concentration is decreasing to 0.25 about millimoles per square meter, cubic meter, the production will decrease accordingly, and the loading of the deep water with organic matter will be only a quarter of what it is now, and it will be like what was in the 1940s, which means that the Baltic Sea can aerate itself, oxygenate itself again, and you can remove the pumps. And how to do it? The general principle here is cooled, pumping high oxygen, low density water into the deep water. In the Baltic, we have a very large reservoir of high oxygen, low density water in the winter water, just above the halocline. And we have earlier computed that you should use 10,000 cubic meters per second. That's one can maybe change. That's a good standard value, I can say. And what should the pumps look like doing this work? They could be forced by wind, waves, electrical grid, diesel. Maybe cheapest. Oil is cheap now. Yeah. Here is the arrangement we used in the Bifjord with a pontoon and 2 pumps. And we took surface water there and pumped down to 35 meters. And one important detail here is that you have to have a good speed to get good initial mixing, because the circulation you create here is very important. It's important that you decrease the density in the cell where you are pumping. But of course also important that oxygen is supplied. Already in 25 we sketched this kind of device, floating windmill with pumps. I don't think this combination is actual anymore if you can do it in just 10 years, and it's better to just pump. Use green electricity for electric pumps. Pumping in the Byfjord looks like this. Pump starts here. You see a very rapid decrease of the density because of the flux into the plumes. Pump stopped here, anoxic water. We got the water exchange here. Density increased again, and the inflowing water had oxygen, and we get it oxygenated in a couple of days. That was the start of the whole thing. Cost 40 million. Cost 40,000 million crowns. Building, running, removing. Minus selling it to anybody else. Of course, you need to do a complete environmental impact analysis, and the question you have to ask you, of course, is: do you want the Baltic to be like in the 40s? Maybe not. Then don't do anything. And we also have, of course, to investigate what happens in the restoration period. We have looked at what will happen with the cod recruitment in the Bornholm Basin. I don't have time to show you the computations, and want to say thank you very much.
Thank you, Anders. Thank you, Anders, for this very nice presentation. We can allow some 2 questions because we are. Please, Heikki.
Thank you very much for the very interesting presentation. I would like to ask you about the budget calculation of phosphorus you showed. So according to your calculations, there would be a net outflow from the sediment of about 90,000 tons per year. Net. Did I understood it right? So every year there would be 90,000 tons from the sediment.
Yeah.
As net value.
As a net, yes.
So if it would be so high value, my understanding there should be a constant increase in concentrations of at least deep water. So could you explain how this? I tried to calculate from the values that according to the concentration changes, the increase would be maybe of the order of 5,000 tons. So where is the rest 85,000 tons? Thank you.
Yeah, there is the increase. And you think that it should be much greater with the numbers I gave you. And actually we got this from using this model. Because you have this is the internal sink, and that is proportional to the concentration, the wind surface concentration and the area. And it's so if you increase the concentration, the internal sink also increases. And that's the reason why the concentration doesn't increase more than it does. And actually, you have this in so the concentration follows in equilibrium this line, and the difference in these 2 ponds is completely according to the model and explained by the increased zinc, which you get when you increase the concentration from 0.8 to 1. So it's from the model.
Okay,
Yeah.
thank you very much. And if I now understood right, there are maybe some shallower areas where this is partly retained.
Yeah.
And it should be then, if it's in deep water, so it must be due to chemical precipitation or?
No, it's not. I think it's mostly in the shallow areas above the deep water.
Above the hallock line?
Yeah.
Okay, so it should be then biological through increased sedimentation.
And some of it is certainly also export to the Botnian Bay, Botnian Sea.
Okay, thanks very much.
Okay, time is flying now. I think we have to continue, unfortunately. But we can discuss, of course, further and also during the lunch break. So,
can I say one thing?
Yeah, sure.
I have a poster downstairs. I was standing there in the afternoon.
Thank you very much.
If anybody wants to ask.
Yes, there will many be there, I'm pretty sure. Okay, we continue now with the next presentation. And this will be given by Bengt Simonsson, Technic Magnat, removing eutrophication-causing sediment top layer from seabed, converting it to valuable raw materials. Please.
Thank you very much. Hi, everyone. My name is Bengt Simonsson. I am the R&D process leader of TechMarket. I will explain what TechMarket is later. And first of all, we would like to please let us expand on the system boundaries for a little while. This project that I'm going to describe will combine the ambition to achieve a sustainable, prosperous domestic farming with the saving of the Baltic Sea. So we're going to expand on this a little bit now. TechMarket is TechMarket is a spin-off from the Royal Institute of Technology. We deal with system integrations in different types, and I would like to show you the first project we did for the Nordic Councils of Ministers, just to emphasize that this matter that we're discussing today is perceived by 540 Nordic municipalities that were involved in this semi-qualitative survey, is perceived as the most important areas of clean tech, that is wastewater purification and waste management. TechMarket is dealing with a lot of different areas within the environmental technology field, as you can see, but we focus today on what we do upstream. We do some development projects that deal with the creation of a new system for single household sewage systems. So we work upstream, and of course, as we're talking today, we also have developed a system for downstream applications. We did a few years ago a project that we called Phosphorus and Nitrogen Neutral Municipality. And some of the information that I'm going to start out with now deals with the expanded system boundaries that we're going to talk about now. And that is phosphorus, the import of phosphorus into the total system. That implies the phosphorus we buy for agricultural purposes. And that totals roughly 10,000 tons a year. And as you know, we continuously work within the agricultural field with improvements to improve the efficiency using that amount of phosphorus. But at the end of the day, only 20% of that phosphorus we import ends up in the food we eat. So we're addressing this, and I have 15 minutes now to describe the idea, what we will do what we're doing in this project. And I will start out to again emphasize that we do two things. We work land-based and sea-based. And the land-based part of this project deals with the fact that we really need to get started with a recycling scheme to stop the import of 10,000 tons of phosphorus yearly. The challenges with 10,000 tons of phosphorus is that, again, 20% end up in the food and 80% end up in a system that we cannot really control easily or at a low cost. So if you just for a moment consider the possibility of retrieving 10,000 tons of phosphorus from the large volumes that we know from what we hide in seabed and also on land, of course. And that's really the core business of this project, is to consider that possibility, to create what we call circular economy. And comparing with the HELCOM objectives, you see that there is still some left to stop the effects of what we're dealing with now. And the objective of the project we are running is about creating a recycling scheme that implies that we're not going to import any more phosphorus into the system. That's what we're doing. And as an extra effect, when we remove this phosphorus from seabed, which in our project consists of organic matter, we also reduce the volume of oxygen-consuming material, so we will have a decrease of a reduction of the internal leakage as well. So this project deals with the possibility of retrieving the top layer of sediment, the freshest top layer of sediment that is causing oxygen consumption and leads to leakage. And what we do is we have developed a machinery that only retrieves the top part. I will explain later why. And if you look at what happens with the top layer, it's very runny. It's like buttermilk, and the layer below there is more like jelly. So it will refill when we remove the top layer. And this top layer, when we do digestion tests, we can easily see that the top layer will generate much more biogas than the layers below. So already here we have a revenue stream. If we remove this layer, we will decrease the oxygen consumption, of course, at the bottom waters. And we will also make use of this energy and convert it on land in controlled processes. Major point of revenue stream. I will show you now, I hope, an animation that will show you the project we're running. Hope this works out nicely now. This project consists of two parts. The first part deals with the circular economy. Who's going to pay this? That comes to everybody who's working in this field. And we have included all the sectors of society that emit substances that eventually cause organic growth in the Baltic Sea. The other part is the technical pre-study, or the technical part of the project. And what you see here is what you can see from the surface. This is a docking pontoon that is used to ship out the retrieved sediments that we work with. If you look below this surface, you'll see the system, the permanent system installation, 1 by 1 kilometer. And this system is placed in accumulation areas, and it's used permanently. In the summertime, we will use bottom water with high salinity and put air into it by the surface and return it back. So we will do that 5 months a year. And that will add some phosphorus to the surface, we believe. April and October, we will retrieve sediment in just the top layer now. And the reason for retrieving the sediment twice a year is that we need the very fresh parts of the sediment. And all this equipment is below 20 meters. We have also developed an application for our friends with a trawler, because he wanted to make a contribution also to the Baltic Sea. So we have a system that he intends to use in Lumpan in Åland to clean up a little bit there. We have a special vessel that will collect the sediment, and on this vessel we'll have some centrifuges that separate wanted matter from not wanted matter. I'll explain that later. And the sediment, the organic part, will be transferred to railway transportation and be shipped to this factory that we have. I'll show you soon. And this is where we produce biogas and fertilizer, which is the idea here. And this production obviously is a very large scale facility, so that we have a good economy in it. So this is a picture showing you what we do with the organic part of the sediment. This is the plant now that I'm showing you. First of all, we digest organic sediment and we get methane out of it. The residue, we will separate solids and liquid parts. And this liquid part we will put through an oxidation chamber, and the solid part we will put through a pyrolysis process. And in this part, we eliminate all the organic pollutants that might be in it. And then we mix the two, and finally we will leach out the heavy metals. So what we achieve here is a fertilizer that is clean enough to put on farming land. So we take away the organic pollutants and the heavy metals. We have done tests now with the different types of oxidation methods, and this shows you the results from oxidation of medical residues, where we have used the toughest fluorochinolones, the toughest substances that long last in nature, so to say. And we also use very smart equipment to separate the different fractions. One of our industrial partners is Alfa Laval, who's providing us with this nice machinery that is called a centrifuge. When we run it with a low G-force, we separate the mineral parts of the sediment, you know, the silt, the inert part, when we talk about biogas. And when we speed this up in the next machine, we will separate the water from the organic material. That's the idea. So this is not a mining find. It's not a phosphorus mining field. We have to increase the concentrations of phosphorus, of course, to make this profitable. So when we look at the energy comparison here with the nutrients, yes, 2 minutes, we see that we still have some energy left to refine if we compare to the energy consumption and what's in the energy of nitrogen, phosphorus, and potassium. The risks now. We don't have any particle dispersion, the reject water is safe, and we don't have any pollutants that will end up on farmland. The risk we're dealing with now is technical failures that will cause leakage, and that areas that we work on turn oxic. What will happen then? That will need to be found out. The financial balance shows that this is a plus minus zero process. We have revenue streams. The product value, biogas and nutrients will represent 75% of the income here, and the rest is emission fees from the sectors of society that I talked about earlier. The way forward now is to start with the leakage that we know. For instance, Lake Lan, number 36 of lakes in Sweden, leaks like 30 tons per year. That is equivalent to all the holiday homes in Sweden. And we look for, in what we call the geostratification now, similar hollows where we're going to find phosphorus in areas that eventually will flip over and be... I will speed up now. Shit, all these nice pictures. Down the drain. Some words just about the financing schemes. We have developed a financing scheme for 3 sectors of society, and we're also developing what we call a flexible emission fee, that we can balance upstream activities with downstream activities. So we're not forgetting about the upstream here. Christoph is very eager to state that type of things, I know. And the way forward is to create this local investment that we can create jobs and create energy production. We have a lot of supporting organizations, a lot of municipalities that go along now, and also projects in Åland, Latvia, and of course Sweden. And the conclusion would be more winners and fewer losers, I hope. Thank you.
Thank you so much, Bengt. Thank you so much. We have time for 2 or 3 questions. Please.
Well, isn't there a risk when you are sort of, I don't know what kind of vacuum cleaner you are using for getting the sludge from the bottom, but usually when you touch sediments with some, say, hazardous substances or phosphorus or anything, there is a risk that you spread the substance all around. So isn't there a risk of sort of getting the phosphorus into the water column? And also, well, I guess there is no risk of having suspended solids, but one would think that there is also this risk of having reductions in visibility and suspended solids going around along with phosphorus.
I understand your question. No. We move faster. We suck faster than we move, so we don't have any clouds there. We have proof. That's the design, really. That's what came to us before we started to design this.
Okay, one more question here.
Thanks, Bengt. I'm Carl-Johan Lehtinen from NEFCO. Thanks for the interesting presentation. But I guess you have thought about this, but metal removal from the sediment is very interesting. Thinking about that apatite ore has high levels of metals when it's taken out from the bedrock. Do you think there would be possibilities of having a premium price for this kind of phosphorus that is recirculated compared with virgin phosphorus?
We should ask Peter here from LRF. I think the fertilizer we produce will contain more micro and macro substances. So maybe yes, but I'm not a farmer. But we will include more than phosphorus, nitrogen and potassium. Yes.
I think phosphorus price right now is about 21,000 euro per ton. So I think anything that comes close to that.
Yeah, well, this calculus I showed is based on today's prices. So if the prices go up, we eventually will be even better off. Okay.
Okay, thank you, Bengt. I think we have to continue now and come to our last presentation of this morning session. It will be Sven Blomqvist from Stockholm University speaking about enhanced inactivation of phosphorus in Baltic sediments by addition of marl. Sven.
Yes. Thank you for the invitation. And this is what we intend to. My talk here is an initiative of the Swedish Environmental Protection Agency, which in some years ago, particularly Siv Johansson and Roger Rydin, they asked us, and us are in this case Emil, Rydin and myself, and we were asked to look for opportunities to enhance the inactivation of phosphorus in the Baltic Sea sediments. That was the task. And they said to us, turn every stone you find. Yeah. Before continuing, I can say that this study has since then been supported by the Baltic Sea 2020 and Cementa, which is a company at the island of Gotland. This task, which we were asked by the Swedish Environmental Protection Agency, was to how to enhance. What can we do? And particularly long-term removal. And here's what I think is the most thought-provoking graph in this case. This is time and 1,000 tons of P in terms of total P. What we see here is the upper curve. This is the inventory, the amount of phosphorus, total amount of phosphorus, which is mobile from 1970 and further on. We can see that the trend is that it is increasing, the phosphorus here, and today we have roughly 700,000 tons of P in the entire Baltic Sea. Quite a lot. Normally, when we talk about the Baltic Sea and the problems, we talk about what is illustrated there by the lower curve, the annual total phosphorus input, which is roughly some 30,000 tons. A small fraction compared to the overall pool of phosphorus. And we see here also, this is roughly 30. If you see that half of that is anthropogenic, we are down to 15. Yeah, 15,000 tons. And that is the fraction which we are doing, taking actions now, trying to reduce this amount, this small amount. Whereas the overall, the large pool, nothing happens. It remains high. And from that was also the reason for looking for alternatives. How can we reduce this upper pool? The traditional idea is from the old days of Mortimer, and that says that the phosphorus concentration is controlled by iron. And that applies to freshwater lakes and certain coastal water, marine coastal waters. If we look into the Baltic now, how does it look? Yes, we have iron, but an extremely low concentration. This is nanomole phosphorus, iron. But when you precipitate and bind phosphorus, you need 2 iron atoms per 1 phosphorus. And that means that you need quite a lot of iron. Nanomole, that's almost nothing. So the concentration of iron is very low. That means that we have an iron deficiency in the Baltic proper. Due to, and the interpretation is that it's a supply of sulfide. The phosphorus concentration is the iron concentration is very, very low because it is bound in the Baltic sediments. This is the well familiar, the black ones. Iron sulfide is the reason for the color there. And in this case, the mechanism which is binding phosphate by iron, is shut off here. We don't have any iron in the water phase, almost in. When the shut off is due to binding of the iron by sulfide. Okay, that means we need something else. We can't rely on a traditional idea of what controls phosphorus. We need another substance instead of iron with capacity to bind and retain phosphorus in the bottom sediment. And from that report to the Swedish Environmental Protection Agency, we have suggested that we might use marl. And marl is a carbonate-rich clay. And that is, marl is a problem. This is from Gotland, where we have a calcium carbonate mining going on. As a byproduct, they get marl. And today, there are huge amounts of marl at the island of Gotland. Roughly 10 million metric tons there at Storungs, which is the place where there are most marls in the heaps. And you see, this is like a mountain. You're traveling around on the marl by car. And we don't want to have it. This is not wise. This is not sound. This is not the way we deal with natural resources. This is not the way. But the question is that, can we use this marl? And what we have done here, we have done a large number of time course absorption experiments. We have crushed the marl into a small fraction and then looked for the capacity for it to bind phosphorus. And what we see here is that this is time, 3 minutes absorption of phosphate. After 3 minutes, almost 100% of the phosphate is bound by this marl. And it appears to be stable too. Here is the experiment running on for more than 1 year. And also we started a certain pilot study. This is a sediment corer, and we took samples, incubated them during 24 hours, and added marl to that, and the p-flux was reduced by 95%, by adding 5 millimeter on top of the sediment. So long, it appears promising. And then the question is, what is the absorption capacity of the marl to bind P into? We have looked here for parameters, the amount you usually find, where it is the saturated, when it's the matter saturated with respect to phosphorus, how much can it bind, and compare that to different specific areas. From that, we can do a rough calculate. How much does this marl can provide us with? This 10 million metric tons in that particular heap. And we say that it appears to be enough to treat all anoxic, hypoxic bottoms in the entire Stockholm archipelago using the matter which we have studied. But we have also found that the P adsorption efficiency might be further enhanced by as much as three orders of magnitude. That is quite a lot. And this means that the marl heap on Gotland should be, in the latter case, be well enough to treat all anoxic, hypoxic bottoms if the entire Baltic Sea. Roughly that area, you know. And that is to very low cost. less than €3 per kilogram P. I don't think you find any other substances where there are approaches with the same economy. Very cost efficient. Okay, the latter one, what is that? Is that tricky? No. It has to do with that we might form calcium phosphate, in this case apatite, which is a very stable mineral. You have it here, for instance, all of us. It's very stable, and it might be formed in the Baltic Sea if you change the ratio between calcium and magnesium. There's too much magnesium compared to calcium. If we change that, we increase it by a factor of 5, the ratio, then apatite, at least in our experiments, is formed. So if we might form it, that might be an opportunity to bind phosphorus, and in a very stable way. Interesting here is that, or essential here to understand it, is that the calcium carbonate is rather stable. There is no release of calcium. No, you know, the island of Gotland, 400 million years old, quite stable. But if you heat it, you produce something called quicklime, calcium oxide, which is very soluble. So it's very reactive and can't be used as it stands. But and this is where our frontier today is, that if you crush that marl and heat it somewhat to form a semi-crystal phase, which can be settled onto the bottom, liberate calcium, and then precipitate as apatite that is bind P in the sediment. This might be an opportunity. And this is also, as I said, this is an X-ray diffraction diagram. What it shows is that we have 3 phases here: calcium phosphate, calcium oxide, and the semi-crystal phase. So when we heat it up to, we have looked at it at a different temperature, 750 degrees of Celsius. We get a third phase, the semi-crystal phase. And if that works, that might be a source of calcium. So we transform it to that phase, we supply the system with that, it settles, and this is getting dissolved, and from that dissolution you might get calcium, and might be then form calcium phosphate, apatite. So, yes. I think we have 2 opportunities and 2 ways to go. We can either work with the marl and then in some way improve the capacity. There are a number of opportunities. We might add certain substances. For instance, aluminum might be there. Also a small amount of it. Or we might transform and create this type of semi-crystal phase, which then might react in a most efficient and cheap way and act as a band phosphate. So 2 opportunities. And by this approach, I think it might, at least theoretically, be possible to reduce the huge amount of phosphorus to the 700,000 tons and bind that into the bottom sediment. Okay, thank you.
Thank you, Sven, for this very interesting presentation. Are there questions to it?
So have you tested this at some
sea depths already? And how do you spread it? How do you use it on the sediment?
No, but we haven't tried that yet. No.
Okay.
That is a business in itself.
All right. And in the heat treatment, you can, I guess, you could kind of load the marl with all kinds of different substances to modify its chemical
be
binding
possible.
properties.
Yes, it might be possible to modify.
That's a science in itself,
yes.
actually.
And
So.
we have financial support here in addition to the Baltic Sea 2020. We have also support from Cementa.
Yeah.
And this is actually what they are living from.
Okay, good.
More questions? Maybe, yeah.
Yes. It is, yes.
The question, you said that the calcium oxide, if you put it into water, it's a very exogenic reaction,
Yes.
producing a lot of heat and
yeah.
what?
And that is the reason why we can't use it. We can't use calcium oxide. But we can't either use the calcium carbonate because that's too stable. And then what we say, okay, in between here somewhere, we might find a phase which might dissolve there. And it's possible if you supply the system with that, it settles and enters into the water, to the sediments, and then start to react. It's a sort of delay for that semi-crystal phase, which we actually don't, at the moment, we don't know what it is. But it is something which is formed from this one, on its way to that. But it's most promising if it works, because what you need is a certain amount of heat. And they have at the island of Gotland and the Cementa, they have excess of that from their manufacturing.
Okay, thank you, Sven. Further questions? If not, then I would like to thank all the speakers from today's morning session. And I